Hello, chemistry students. My name is Kim, and I'm here to talk about endo and exothermic reactions in the context of potential energy diagrams. So our learning goals for this video are to define endothermic and exothermic reactions, to identify a reaction as endothermic or exothermic based on its potential energy diagram, and to identify a reaction as exothermic or endothermic based on Table I of the New York State reference table. You're going to want a digital or a physical copy of the New York State reference table with you for today, and you're definitely going to want some note cards or at least a piece of paper to take notes on, as there's a couple of key concepts that you're going to want to write as we go through this video. Let's review an exothermic versus an endothermic reaction. In an exothermic reaction, the prefix exo means outside. Energy is being transferred out of the system, into the surroundings. So exo means outside. In an exothermic reaction, energy is being transferred out of the reactants and into the environment. This means that the reactants are releasing energy to become products, and the products will have less potential energy than the reactants for an exothermic reaction. Reactants release energy to become products. Oftentimes this reaction will release heat or light, some form of detectable energy, and the products will have less potential energy than the reactants after that energy has been released. An endothermic reaction is the opposite. The prefix endo means inside, so energy is being transferred into the system from the surroundings. The reactants are absorbing energy to become products, and therefore the products have more potential energy than the reactants. The heat of reaction, or the delta H, for an exothermic reaction is negative because the amount of potential energy in the reactants is decreasing as they transition into products. It's the opposite for an endothermic reaction. The heat of reaction is positive because reactants are absorbing or gaining energy as they become products. Let's take a look at Table I of our reference table. Table I shows the heat of reaction at standard temperature and pressure, 101.3 kilopascals and 298 Kelvin, for a series of reactions. These delta H's, or heats of reaction, represent the change in energy, and they represent the forward reaction that is being shown. For now, let's focus on going through Table I as it is right now and try and determine which reactions are exothermic and which are endothermic. Pay close attention to the bottom annotation underneath Table I. This is always here to remind you a minus sign indicates an exothermic reaction. This means that using the process of elimination, a plus sign must indicate an endothermic reaction. So they actually tell you right there what the answer is. Endothermic is a positive delta H, exothermic is a negative delta H. And so if I were to categorize each of the reactions on Table I, this is how I would categorize them. There are more exothermic reaction examples than endothermic reaction examples here. Let's do a practice problem based on Table I. This question says, based on Table I, which compound dissolves in water by an exothermic process? Now don't be worried. I know that if you look at Table I, you don't see anything that says dissolving. But remember, when you see an arrow with H2O above it, it means the process is dissolving. So we are looking to compare NaCl, right here, with NH4Cl, with NaOH, with NH4NO3. So we are comparing and seeing sodium hydroxide, ammonium chloride, ammonium nitrate, and sodium chloride. Which one of those compounds is dissolving by an exothermic process? Remember, a minus sign for the delta H indicates an exothermic reaction. So if I look, the only of those four options that has a negative delta H is sodium hydroxide, NaOH dissolving. So my answer is 2. Let's do one more practice problem based on Table I. So based on Table I, which equation represents a reaction with the greatest difference between the potential energy of the products and the potential energy of the reactants? Then it gives 4 different reactions: the synthesis of aluminum, the synthesis of water, the combustion of propane, and the combustion of glucose. So this seems like a very scary question until you realize that Table I is giving you all the information that you need here. We just need to locate each of these reactions on table I. So if I take a moment to find all 4 of these reactions, there they are. Let me go back and look at what the question was asking. Which equation represents a reaction with the greatest difference between the potential energy of the products and the potential energy of the reactants? So all 4 of these reactions are exothermic. They all have a minus sign in front of their delta H, and the biggest number is negative 2,804 kilojoules, which is the combustion of glucose reaction. So the answer to this would be number 4. Let's think about how the potential energy diagrams would compare for an exothermic versus an endothermic reaction. In an exothermic reaction, energy is being released, and in an endothermic reaction, energy is being absorbed as reactants become products. So in an exothermic reaction, to get from reactants to products, we need to move down on the y-axis. Whereas to get to reactants to products in an endothermic reaction, we move up on the potential energy y-axis. So a good first step when you're trying to determine whether or not a potential energy diagram is endothermic and exothermic is to just ignore the curve in between. I haven't even drawn the reaction curve yet here. Ignore the curve in between and just look at the relative positions of the reactants and the products on the y-axis. If you have to move down to get from reactants to products, energy is being released as reactants go to products. That is a negative delta H. If you have to move up on the y-axis to get from reactants to products, again, ignoring the reaction curve in the middle, then energy is being absorbed, and you have a positive heat of reaction or a positive delta H. In an exothermic reaction, the reactants with more potential energy are less stable than the products, which are more stable because they have less potential energy. It's strange to think about, but remember, stable just means how likely you are to change. And so an object with more potential energy is more likely to change, which means that it's less stable. It's the opposite in an endothermic reaction. The reactants are more stable than the products they are becoming, and that energy is being absorbed to add potential energy to make those products less stable. Now let's add back in those reaction curves. Remember, in both an endothermic and an exothermic reaction, there often is an activation energy hump. That does not change whether or not the reaction is exothermic or endothermic. So look at the exothermic reaction. It is an exothermic reaction because to get from the reactants line to the products line, you need to move down on the y-axis, even though first you have to go up to get over that activation energy hump. Right? You still ultimately are moving down to get from reactants to products. Notice how that is different than the endothermic reaction, where you move up to get up the activation energy hump, and then you stop and finish at a point that is still higher on the y-axis than the potential energy of your reactants. Here's a summary, including a sketch of potential energy diagrams for both exothermic and endothermic reactions. I strongly recommend that you take these notes down and also that you consider making yourself note cards or some other way to quiz yourself to remind yourself which of these characteristics relates to or matches back to an exothermic reaction and which relates back to an endothermic reaction. And now for some quick practice. Decide, is the forward reaction of this reaction coordinate diagram endothermic or exothermic? This reaction would be exothermic. The reactants have less potential energy than the products. Let's try another. Is the forward reaction of this potential energy diagram endothermic or exothermic? This one would be endothermic because the products have more potential energy than the reactants. Let's check back in on our learning goals. Hopefully you feel more comfortable doing all of these tasks. There's actually going to be one more video that you can watch that is going to be me going through practice Regents questions that involve potential energy diagrams. There's a lot of those that can seem more confusing than they actually are, so I highly recommend you checking out that additional video of extra practice after you watch this one. Nice job.